Today's language AI has made remarkable advances in the last decade, but it's still not good enough to read, understand, and deliver answers with intelligible explanations for why those answers make sense. I've always thought that AI should become collaborative and intelligent thought partners that can read, understand, and communicate in our language. That AI can provide consumable explanations that justify its responses, ultimately help us solve problems and make informed, responsible decisions. This is not a new vision for AI. It's probably 60 plus years old, but still highly relevant and yet unrealized. Arguably, the crop of AI today doesn't learn to understand language at all, not the way we mean it. And it's not entirely clear that on our current course and speed, we will get there. At least in part, this relates to how we define understanding and how we measure the performance of our AI against that definition. To ultimately crack the nut, we need to focus squarely on what we want machine understanding to do, and then to effectively measure it. I'm not sure we've done that well enough yet. I have some thoughts as to why, and I have some ideas on how to better move toward that vision. When you look at the tasks that we have been using to drive progress, it's not clear to me that we set ambitious or holistic enough benchmarks. Maybe it's because we are targeting a different problem, or the more ambitious goal of understanding is too subjective to define and expensive to evaluate. Maybe it's just too hard, and slow progress will make us look bad, or at least the not ideal for the academic paper mill. I don't know the answer. A mix of the above, perhaps. We might just step back and ask ourselves, though, where precisely do we want to go, and are we doing the things needed to measure the right sort of progress? How we define and measure progress has an enormous and primary influence on what gets done. The benchmarks we create de facto define the vision more than any mission statement possibly can. As we are well aware, the metrics are how the mission gets operationalized. If we measure how well systems mimic human utterances as reflected by a corpus, then at best, that is what we will get. The open question remains, is that in fact a surrogate for measuring understanding well enough to answer questions and reveal the logic used to derive those answers, ultimately in a way that other humans can comprehend? That's a taller order. Why not measure that more directly? For hard problems, it often makes sense to creatively break it down into component pieces. These components get their own metrics and can often get a life of their own. But if we don't demonstrate how we built it back up to perform on the broader vision, then we end up with a bunch of piece parts that may perform well on their own, but still fail to solve the intended problem. When working on Watson to win at Jeopardy, we had over 100 engineered feature generators, including, as you might imagine, a semantic parser. I would shift resources around to the different feature generator projects that look more promising when integrated with others. So I'd make sure they were integrated with others and then test the end-to-end result. If they looked promising, then they got included. When the parser team wanted more investment to increase parser accuracy, I said, well, given all the other features, how do we know it will even matter to the system's answer accuracy or confidence? Do an experiment that assumes perfect parsing and tell us what happens. There was no impact. In the context of all the other features and the end-to-end system, the parser was apparently good enough. That was, of course, unsatisfying for the parser team that wanted to beat the latest parser benchmarks on a standard data set and get another paper published. This story played out over and over for many of the different components. So much so that to make component research investments, we would first do what was called a headroom analysis, where a simulation was performed to assume the component could do as well as the researcher hypothesized. We plugged the simulation into the larger system and measured if Watson won more Jeopardy games or not, the final goal. If it did not, we would invest in other more promising ideas. Sometimes it was cheaper to do the work rather than the headroom experiment, but nonetheless, the metric used to shape the investment had to be the fully integrated end-to-end metric. Always doing the full end-to-end test to measure the potential impact of any component research was more expensive from the component researcher's perspective. It was also challenging for the team. as no individual or component research goals were considered independently valuable in their own right, at least not for what we were doing. So individuals, rather than being committed to a specific research area, had to learn to contribute more broadly and to be agile. They had to shift to ideas that seemed to be gaining promise. Everyone was rowing in a single direction with the same incentive, with a clear, measurable, albeit hard metric to achieve. In the early days, the system was so bad, it was so very discouraging that it led researchers to want to focus on their individual component metrics and to publish on those. Keeping the team hopeful and focused through those times was, of course, a management challenge. The principles that resonated were: have a clear and ambitious vision, define what we really want with no regard for the methods that may or may not work, set realistic expectations for how hard the problem is, in order to make the right level of investment and to develop a sense of how difficult it will be to do and to measure. Think holistically. Like, you're always going to have to creatively decompose any sort of hard problem to solve it, but always put all the pieces back together and judge based on the holistic performance. Even, for example, the UI UX can change how we architect the guts of an intelligent system. So always think holistically end to end and measure that. The benchmark's cost should be less than the expected value of success. So it needs to be valuable. So build tests for the big vision based on expected value. So if this test seems too expensive, maybe the vision is not ambitious enough, or maybe it's believed impossible. So thinking about expectations, how hard is language understanding? I think it's really hard. When I look at the history of AI, for what it's worth, you can read papers from 1969 about the second generation of natural language question answering systems. But when I think about that, I want to step back and reflect on the fact that basic NLP is remarkably better than it had been for decades prior. We've made enormous advances. But are these technologies really designed to solve the problem, to solve language understanding effectively? Maybe. Maybe they're solving, parts of the problem, of a problem that I might consider a much more complex one. Maybe there is a transformer-based model that will produce satisfying NLU, but I suspect the bigger problem is figuring out what the adequate training data looks like and how to efficiently acquire it. Regardless, the point is, are we clear on what we want? Are we realistic about how hard it is? Are we really testing to achieve it? What if real natural language understanding does not emerge from extrapolation of word usage in existing corpora? What if we lack the type and quantity of data we need to learn how interpretations of language are used to deliver answers and explain how those answers are derived? What if all of that is in fact not latent in our corpora? Personally, I don't know. Maybe, maybe not. But more importantly, how would we know? How do we tell if we're getting closer to the goal if we set up tests that perform well under those assumptions, but fail under more ambitious ones? I think when we invest in benchmarks, we have to be careful to know what we want versus what it looks like we can do, and then define what good looks like and measure against that goal. I am not sure if we have a good sense of what we really want from NLU systems. Perhaps good looks like humans making better decisions based on confidently learning from interacting with machines that educated themselves from vast quantities of content. That sounds like a high bar. Then again, maybe search engines already solve the problem. They deliver understandable content and sometimes do a great job of explaining stuff and help me make better decisions. The right YouTube video can do wonders in helping me understand and make better decisions. I'm being just a tad flippant to make a point. We need to think about what problem we are really solving and for what expected value in order to justify what might be a longer road and more expensive benchmarks and data sets. If we really want machines to produce understanding, I might start with what we mean by understanding. I like this definition. The interpretation of a particular situation in order to provide the context, insight, and foresight required for effective human decision making. I mean, I like it because it focuses the effect on human decision making. It doesn't define understanding independently of what humans do with it. They use it to make better decisions. It also suggests that an understanding is transparent and enabling, and that it offers up the context and insight required for the human to make decisions, as opposed to offering the answer that the human just adopts. Of course, this also implies that the ability to produce a good understanding may be somewhat subjective and therefore expensive to measure. We end up defining an understanding as an external artifact, not an internal construct, one that is judged based on the effect it has on others' ability to comprehend and apply it. So, language understandings is, when we talk about expectations, especially given a definition like that, it's probably really hard. I mean, humans, despite being able to read and generate language prolifically, work hard to understand each other for any sufficiently complex topic. We spend huge amounts of effort in nearly every field trying to build understanding. And it is still difficult to know to what extent we understand each other in the end. Understanding almost becomes a social artifact, again, an external construct through which we can communicate and get our thoughts aligned. Often only actions or continuous probative dialogue helps determine the quality of the understanding. Again, we see this in every field. There's often an interactive and creative process where understanding is refined, justified, developed, and judged as part of a continuous dialogue. So I don't know about you, but reflections on how humans create and refine understanding seems to go well beyond what we have today, well beyond, I think, answering multiple choice questions for children's stories. But to be clear, even doing that well, where it can better reflect an understanding, might be good enough, might be I shouldn't say good enough, but a good proof point, along the way. So I don't want to discourage starting with children's stories, but I think it's a good question of whether or not answering multiple choice questions, or at least how we develop those multiple choice questions, is that good enough to move us along this road where we can judge machines as really understanding the underlying content. This is an awesome cartoon. I can't resist, so let me just act it out. How do you not understand this? I explained it perfectly. Oh, maybe your notion of perfect explanation should include person I'm explaining to understands it. The cartoon suggests that a good understanding can produce an explanation that is predicated on who is listening. The understanding is only good if it can be understood and used by others. Doing that well would require some consideration for any prior model that the listener engages in to aid in, or actually bias, their interpretation of the explanation. So a system that can generate and communicate a good understanding might be judged better if it can learn and adapt to the end user's relevant prior models. How do you do that? That sounds hard. That sounds a lot harder than understanding a multiple choice test, or answering a multiple choice test. Maybe it's too ambitious. Does it fit our research agendas? Is it what we really want? Even if we believe it's too hard or too ambitious, I suggest it's still worth defining and fitting onto a roadmap so that we can create the right benchmarks for the right steps in that roadmap. If machine understanding systems are held to provide good explanations for how or why an answer makes sense, then we have to have some sense of what makes a good explanation. Again, another hard thing to work out, I suspect. Here's a question that predictive systems work hard to answer, and for potentially high reward. Are we headed for a recession, and why? Both of the following answers are yes, but they have different explanations. The first one gives the explanation that essentially says, the data looks like it did before when recessions happened. Yes, the most reliable forward-looking indicators are now collectively behaving as they did on the cusp of full-blown recession. This is courtesy the Signal and the Noise by Nate Silver, by the way. The second answer explains causal market dynamics that applied in this case, and that actually lead to a recession. So yes, consumers have expended too much credit to pay for their homes that the housing bubble had made unaffordable. Many, realizing they were overcommitted, stopped making their payments. The defaults are likely to result in substantial losses for the banks. The degree of leverage or debt in the system would compound the problem, paralyzing the financial industry. Without access to money in the form of credit, businesses reduce expenditures. Consumers with debt and expectations to make less money further reduce spending. The drop in demand is likely to trigger a recession. What do we want AI systems to do? Which one reflects a sufficient or adequate understanding? Does the difference between these two types of explanations matter? What performance best reflects our goals? Would the preference for one type of explanation over another change our system design? Whatever your answers, they should drive the benchmark design for what we want systems that understand language and can produce good explanations and transparent explanations should do. Another challenge we face is the tendency to assume task performance is suggestive of progress on a larger goal, and then consequently to misdirect investment. If we do that, at least let's do that transparently with an awareness that while the task is looking good and may be independently valuable, we may not actually be making progress on the larger goal. As we analyze system performance, even individual errors that do not affect aggregate task performance can reveal that we may have lost sight of the larger ambition, or at least that we clearly lack the right benchmark for it. I'm sure you are familiar with these hacked images or adversarial examples. Here we have an ML model confusing the second Persian cat for a toaster, and it's quite sure about it too. Deep neural nets have resulted in phenomenal image recognition performance. Over the last 10 years, progress has been remarkable for any given task, often outpacing humans on the aggregate stats. But when you look at these errors, whether they are practically problematic or not for a specific application, they can be revealing as to what's going on. Statistical success on an aggregate metric might suggest the machine understands the image the way we do. But just a few failures like this can quickly illustrate that this is not the case. In this situation, whatever model the machine has learned produces a very different understanding of what makes a Persian cat a Persian cat. Human models would never result in mistaking the second image for a toaster. Now, to be fair, of course, the system was trained and measured to classify images according to the annotated data and not to build a compatible model for recognition that humans can understand and share. Those turn out to be very two different tasks. So no real foul, unless, of course, the goal was to be able to produce an agreeable justification for why the image was classified as a toaster or a Persian cat. These telling errors can quickly reveal we may have created a great image classifier, but in case anyone was confused, we likely did not create a machine that produces an explicable understanding of these images, one that humans can share and are transparent. That would require a very different sort of benchmark. Spelling errors are not limited to image recognition, of course. You have similar issues when looking at language model performance and how it's used in question answering. The boy approached the turtle pulled itself into its shell. Question, why was the turtle afraid? Answer, because the boy was carrying a large, sharp knife. The answer is in the form of a because, but it looks like the machine has no idea what is really going on. And it's parroting words around fear and generating a plausible structure. A good guess for not understanding. Unless, of course, it thinks that turtles, in fact, understand and generate fear in response to the threat of big knives. What do you think? Here is another question, and the system appears elaborately and confidently wrong. John put the sandwich in the lunchbox. He put the lunchbox in the car. Question, is the sandwich in the car? No, lunchbox is in the car, and the sandwich that's in the lunchbox. Again, makes you wonder, what problem is it really solving? Is it intended to solve the problem of understanding? And define exactly what problem we really want to solve. While these techniques can be extremely powerful depending on the application, are they really achieving the goal? And what metric would allow us to determine that? Soon after Watson won at Jeopardy in 2011, I left IBM in 2012. Watson, while did not have the benefit of massively trained language models, it in effect acted similarly. Rather than raw features, though, we designed and engineered hundreds of features to predict an answer to a Jeopardy question. Those features looked at word context, multiple parse trees, parse alignment, question classifications, decomposition features, many shallow semantic features, source features, etc. We fed them into a series of machine learning models that predicted answer ranks. We ran thousands of full end-to-end test games, and after 4 years had a 73% chance of winning against the best humans. We won. It was a great demonstration of factoid question answering over unique language. But in the end, we researchers knew Watson did not and could not produce and communicate an understanding. With NLU as the primary goal, in 2015, I got back in the game when I started Elemental Cognition. With today's massively trained language models, a factoid question answering system better than Watson would be a heck of a lot easier to build. But it's not clear that as a community, we are any closer to the natural language understanding goal. At EC, we tried to lay down a foundation for capturing and measuring machines' ability to understand, even at the most basic level. We just tried to capture, first, a very high-level framework that one might use to produce or to judge an understanding of a simple story. So the template of understanding, it essentially generates a collection of specific questions for any given story, whose answers together would reflect a basic understanding consistent with cognitive science research. Essentially, the template of understanding drives the generation of questions that end up asking for every agent, object, action, location, and event in the story, who or what did what, where, when, why, and how. So for example, it'll generate all the spatial questions, where each entity in this story is relatively positioned and oriented throughout the text relative to other entities. Or a set of temporal questions. What events and states occur with what relative timing? And then a set of causal questions. How did the events and states mechanistically lead to other events and states described or implied by the text? And then motivational questions. For every agent, how do their beliefs, desires, goals, and emotions lead to their actions? Finally, an evaluation approach was based on the idea that we would have human annotators generate and answer all the template of understanding questions. In effect, producing a spatial map, timelines, causal graphs, plans, and motivational graphs for each story. Well, this doesn't capture the extent of human understanding, what mental models would be built by reading a story. We claim that it is the floor, a necessary part of a robust understanding. If we don't understand this stuff, we don't understand the story. And if you couldn't produce this class of understanding for simple content, it would be unlikely, we claim, you could do this for even more complex content. Here's an example story fragment. One day, it was raining. When Ellie arrived, Rover ran out the door. He barked when he felt the rain. He ran back inside. Annotators write a record of understanding as a semi-structured document that answers all the questions covering all the spatial content, for example, where Rover and Ellie are at different points in the story, all the temporal content, what events happened when, a causal or motivational content, which would be, for example, an explanation for why Rover runs inside. The record of understanding documents can then be used to either, one, have humans or automated scripts evaluate a system's output directly against the record of understanding, or ROU, or the document can be used, perhaps less convincingly, but more cheaply, can be used as the basis for creating a more standard and thorough multiple choice test. As a starter, that is what we did. The idea was to see if this benchmark concept might challenge the state of the art in machine reading comprehension, to see specifically whether systems that do well in current MRC tasks can in fact produce this type of understanding. While we prefer free-form answers to better test explanations and explicability, to quickly test existing systems, we built a multiple choice data set driven by our template of understanding and using the race corpus, which is a machine reading comprehension data set that uses simple stories. We had an annotator write out full records of understanding. Then to facilitate testing existing systems, we generated about 200 race style multiple choice questions covering all the statements in the ROUs. Now, the examples here are basically two versions of the same question. That's because we wanted to mitigate the artificial easiness of multiple choice, where patterns in wording and distractors offer cues that won't generalize. So we created groups of questions about the same content called variant groups. A variant group, we thought, would let us assess whether pieces of content are comprehended more reliably. They gave us a stricter scoring option, where failure on one variant question means failure on the whole group. We put this test to XLNet, a pre-trained transformer model that was near state-of-the-art on the race tasks when we ran these experiments last December. XLNet did better than chance, but as you see here, are considerably worse than humans we tested, who scored over 95%. When we scored variant groups as all or nothing, humans stay around 95%, but XLNet dropped dramatically, which suggests that at least some of its per question performance was based on shallow cues that did not generalize or reflect deeper understanding. This was just a small proof of concept experiment, but essentially, given that multiple choice is artificially easy, it strongly suggested there's plenty of work to get AI systems performing well, even on our template of understanding, which we think is still a floor, but better represents the NLU vision. To be clear, we still think this template of understanding test is a weak test for understanding. We think a stronger test would open up the evaluation to allow for full text responses, even graphical responses and interactive dialogues, or might further require that human users have a task to perform where the interactive understanding presented by the machine is empirically shown to help humans make better decisions. To sum up my views, language understanding is a hard but worthy goal for AI. Let's design benchmarks that acknowledge that and ultimately operationalize and help us advance toward a more ambitious vision. Thank you.